Hello, good afternoon, everyone. Hope everyone is here, 4 p.m., almost the last talk of the day. I hope I can keep the enthusiasm up, a little bit of, the interest up, at least. Well, if you're here right now, it's because you want to hear a little bit more about Kubernetes, AI, wildfires, and how we build a cloud-native infrastructure for wildfire protection at Overstory. My name is Andrea Giardini. I work as an independent cloud-native consultant and trainer, and Overstory has been one of my clients for a long time. They're an amazing group of friends, people, and colleagues based in the Netherlands, but they operate remotely all over Europe and all over the world. In there, I'm part of the SRE team, so I take care of the infrastructure that runs all our jobs and pipelines and so on that we use to prevent wildfires. Wildfire is an interesting theme. We don't think very often about wildfire, their impact, and how they affect our communities and our lives. The truth is that wildfire are incredibly devastating events. You might have heard that earlier this year, there was a huge wildfire in Los Angeles, in the US. This was a devastating wildfire that brought a lot of suffering and loss throughout the community, throughout their businesses, throughout their families, and the aftermath of that will take years, if not decades, to recover from. Wildfires is something we don't think about in terms of prevention. Very often we are good and we have plenty of processes to try to, basically contain a wildfire once it spreads out, but we don't do as much as we should to prevent those wildfires from happening in the first place. Just to give you an idea about the wildfire that happened in Los Angeles earlier this year. This was called the Southern California wildfire. There were around 29 people died, over 200 people evacuated, around 18,000 homes got destroyed, and more than 27,000 acres of land burned down. These numbers are impressive, they're huge, they're also very difficult to imagine. What does it mean? Well, let me give you an idea of what 27,000 acres of land burned means. This is a map of Zurich, so this is the equivalent of 27,000 acres of land. As you can imagine, this brings a great deal of destruction to many people. And you might be interested in knowing, and many of the things that I've learned about wildfire are due to my collaboration with Overstory, is that, especially in California, the cause of wildfire is for 60% caused by defective power lines. So, energy companies have power lines that spread all over countries and different regions and, different types of power lines and so on. And over 60% of the most destructive wildfire in California have been caused by defective wildfire. And the wildfire that happened in California earlier this year, it was not even the most destructive one. Back in 2018, the Camp wildfire burned down over 153,000 acres of land, over 3 times as much. Wildfire prevention, by all means, it's not an easy task. There are many factors in place. There are many things that affect our ability to prevent wildfires. And right now, I'm just going to, you will find this very interesting as well, because it's something that I've learned as I started working with Overstory. Some of these problems are very obvious, but it's something like, oh, I never thought about that. The first thing is that power lines are complex, and they are a critical part of our infrastructure. Electricity that comes to our home is essential for our day-to-day life. Certain structures, like hospitals, need certain guarantees in terms of electricity, and so on. And this network brings electricity to our home 365 days a year, 24/7. Failures are sudden and catastrophic. Just a couple of months ago, a power substation, so not even one of the main ones, failed at the Heathrow Airport in London. This caused over 1,350 flights to be disrupted, and over 300,000 passengers got affected. And again, this was not even one of the main power stations. It was a small power substation that had a sudden failure. So whenever this failure happens, they are sudden, they're catastrophic, and they have a very big impact. In this case, Heathrow Airport was closed for 24 hours, which, as you can imagine, has a huge impact on the people that need to fly, and a huge economical impact as well. Also, power lines are subject to atmospheric agent. They can get damaged over time. And inspecting them for maintenance is not as easy as we think. Until now, the way of doing inspection for power lines was basically just sending people to check those lines visually. But very often, power lines cross also private property. So you need to get the permission to go into a private property of somebody else to inspect those power lines. And that's not always as easy. So Overstory approaches this problem in a different way. Rather than looking at power lines from the ground, we look at them from the sky. So the idea here is that we focus on utility companies that provide energy to our communities, and we use satellite images, or better, a combination of satellite images and the aerial images to create a sort of like risk profile. So we monitor their grid from the sky, from the satellite, and whenever we notice that a certain line or a certain area has an elevated risk of wildfire, we notify the energy provider so that they can go and trim the vegetation before the problem gets out of control, before a wildfire spreads out, for example. So we focus specifically utility provider, and we focus specifically on vegetation management. So the idea is power lines are passing all over the place. When the vegetation gets too close to the power lines and there is an elevated risk of wildfire, we notify the energy provider so they can go and trim the vegetation before a wildfire spreads out. We do that combining a couple of different informations and running our own algorithms on them. First of all, we get the data, right? We get the actual satellite data. And here we use a combination of different satellite images. Some of them, they have resolution as high as 15 centimeters. So using the satellite data, we can do things like detecting which trees are present on the ground. Some of them grow faster than others. Some of them catch fire easier than others. Some of them are more fragile than others, and so on. We get the tree height, the health, the free species, and so on. Then we combine with this data with information that we get from the energy provider. So the energy provider gives that information about their network, their energy networks. Where do they have poles? Where do they have lines? How long are the lines? How much electricity is going through those lines, and so on. And then, combining these two with the algorithms that we have built over the years, we create sort of like a risk profile. So the utility companies are able to see which parts of their network have an elevated risk of wildfires compared to others, and they act accordingly so that the wildfire spreads out. Remember that we're doing wildfire prevention, so we don't act once the wildfire is spread out, but rather we do a preventative action. So let's get a little bit more technical now that we've specified the problem. And here I'm starting from the early days of Overstory. Keep in mind that this is a startup. We started like a couple of years ago, around 15 people. I think right now we are going around like 80 to 90 people involved in this project. When we got started, as a startup, you break things and move fast. So we were using just two things pretty much, Kubernetes and Jupyter notebooks, a lot of Jupyter notebooks. So we come from a background of like data scientists and data engineers, so we were using Jupyter notebooks all over the place. All our transformation algorithms and so on, it was all coded into different Jupyter notebooks. So our data scientists could pretty much go on our web page, select the container image that they wanted that contained all the libraries that they needed, select the machine that they wanted, a small one, a big one, with 1 GPU, with 4 GPUs, and so on, and pretty much run their experiments. This is how we started. We started really with the basics. As you can imagine, this didn't scale very well as the company started to grow. In particular, repeatability and tracking was a nightmare. Questions like this were not uncommon on our Slack. Does anyone have a copy of delivery 24037 TMP4? Or which machine did we use to run this particular notebook? Or which version of this library have we used to run this notebook? The whole process was very manual. And whenever a customer was requesting a scan, we needed pretty much to assign one person per customer to do the job manually and go through a Jupyter notebook step by step. This was impossible to scale. So at a certain point, it was time to automate and do things in a different way, do things better and try to make things a little bit more repeatable over time. We wanted to get more customer, so we could not afford anymore to assign one person per customer. So the two main objectives that we had was, first of all, getting rid of Jupyter notebooks. They're fantastic for exploring data. They're fantastic for playing around and trying to understand the data you're working with, but they're very difficult to maintain, very difficult to test, and tracking them with Git was pretty complicated. Do you know what's the backend of like a Jupyter notebook? What is a Jupyter notebook? It's just a giant JSON file, pretty much. Yeah. Ask me how I know. And then we decided, of course, we needed to automate these workflow runs. It was not possible anymore to work on a one-to-one basis. And so we started looking around for data and workflow orchestrator. We tried a couple of them, even some popular one like Argo CD workflows and so on. Finally, what we landed on was a project called Dagster. Dagster is an open source project that we've been using and contributing to for a number of years. That I personally really like, especially from the cloud side of things. I'm not so much of a data guy. I'm more of a cloud guy. And I really like the approach that Dagster takes in many of its concepts and in the way it works. So the first selling point is that it's open source. So you can install it and use it on your cluster. It has a Helm chart, so it's pretty nice. It has fast development, meaning that you can spin it up locally very easily. You don't need to read 50 different blog posts just to understand the structure of your project. It is very easy to test locally. It works with native Python, so you're basically just creating a Python module that you can import even from different places. And finally, like the selling point for me is that it's a data orchestrator, a workflow orchestrator, which has cloud native in mind. And I will show you in a second what I mean with that. We started running Dagster inside our Kubernetes cluster. We're based on Google Cloud, so we run on GKE. And this is a classical Dagster architecture. So you have a web interface where your user can see the pipelines that are running, which one are stuck, which one are having problems, and so on. Look at the logs, etc. You have a pod, which is a Dagster daemon, which takes care of scheduling your runs and your workflow on certain targets, on certain conditions, for example. And the deployments below, in the Dagster world, are actually called code locations. And with a code location, what I mean is just a collection of pipelines and workflows that is managed by a team. So every team in our company can write their own pipelines and workflow. And whenever they want to create a new workflow or modify an existing one, they have their own code location that they're going to modify. So it's just like releasing a software. You create version 0.1.2, you deploy it to staging, then you deploy it to production, and whenever you deploy to production, it will be available for everyone else. The nice thing is that it's very much like a microservice architecture. So every team is responsible for one or more code location, and there is no way a team can affect the pipelines of another one, just because the pipelines are stored in a completely different repository, in a completely different code location. So these pipelines are grouped by team and grouped by purpose, and each one of them is separate from the other ones. This allows team to have a very direct visibility and ownership over the pipelines they own, pretty much. Another thing that I love about Dagster, the idea of I/O manager. As you work with data, storage is a big deal. Where do you get the data from, and where do you put your data in, right? Dagster abstracts the idea of storage, pretty much. This means that I can have the same pipeline with the exact same code running locally or in the cloud, and Dagster will take care of this abstraction. So if I'm running my pipeline locally, Dagster will use my local file system to save all the temporary files, to save the input file and the output file. Now I can take the same code, bring it to the cloud, run it in Kubernetes, and the whole thing is happening, but now my data is coming from GCS and is stored in GCS. It's read from S3 and stored in S3. And I don't need to modify a single line of code inside my pipeline. You want to abstract how you store the data from how you build the data. This is an interesting one as well. It's also talk that we had before was was talking about this. In the past, when we were running things on-prem, data was more or less always the same thing. It was either a file on an NFS storage or a database. There were like a few options, really. But as we work in the cloud, this is becoming more difficult because now data can be a lot of different things. Data can be a table in BigQuery, a file in Google Cloud Storage. It can be a database. It can be stored in Snowflake, or it can be imported using a tool like a DLT Hub. So data now, in the cloud world, has many different shapes. And many tools, what they do is that they focus a lot on how data is built, but they don't focus much on how data relates with each other. So understanding how is this BigQuery table related to this file in Google Cloud Storage is not as easy with a traditional way of running data pipelines, tools like Airflow. Is anyone using Airflow here? Can you raise your hands? Anyone happy using Airflow here? There is like one half hand. But yeah. In Dagster, what they do is that they wrap this into in the concept of assets. So in Dagster, everything looks like an asset. In here, we have two different pipelines, I guess we can call them this way, that use the idea of assets. And as you can see, those assets are completely different things. So in the top, we have Arbeit pipelines, so importing data from somewhere else. Then in the middle, we are processing those pipelines using a tool like dbt. And then finally, at the end, we run our forecast model using Python, or maybe use TensorFlow to predict our orders. Keep in mind how Dagster shows you not how data is built. I don't know how Arbeit does that. I don't know how dbt does that. I don't know how Python does that. But I know that if I change something in the user cleaned dbt, this is going to affect my daily order summary and my order forecast model. It's very easy to see from the web interface how data relates with each other. Over time, as well, we started building our own extension to Dagster. This is something that we have working as of now inside our company. It's a library that we call the Maple. We have this tradition of calling things with the name of trees. So Maple was this one. And you can think of a Maple op like a step in your pipeline, okay? So the nice thing here is that developers have the possibility to specify the resources that they need to run their pipelines. So in this case, what I'm saying is I want this step to run on a node which has a single GPU that has at least 32 CPUs and around 390 gigs of memory. And we also assign to it a scratch space. This is basically a volume that is created dynamically where they can store temporary file while they're processing. So in this case, it will have a 150 gigs volume attached dynamically where they can store temporary file while they're processing it. This was the first iteration of Maple. The idea in the future would be to rewrite it a little bit better, because right now, as you can see, there is a lot that is Kubernetes specific in this. And the idea would be in the future to abstract it away. It's still, like I don't want my developers to know what a request CPU, request mem is, or what a node selector is. Ideally, we would like to abstract it away in the future with the next iteration of the Maple library. What is also possible using Maple and using Dagster in general is to structure your pipelines in different way. So you can either say, well, single pod, single node. So I can have a pipeline that is really long, but it's all using more or less the same amount of resources. So in the first case, single pod, single node, I reserve 4 CPUs and 8 gigs of memory, and then I'm using the same 4 CPUs and 8 gigs of memory for all my steps, pretty much. Or what I can do, if I have a pipeline that is a little bit more complex, or I have a pipeline where every step takes a considerable different amount of CPU and memory, I can now say, for example, that step number 1 takes 4 CPUs and 8 gigs of memory. But step number 2 needs 16 CPUs, 32 gigs of memory, and it also needs a GPU. While step 3 needs 8 CPU, 16 gigs of memory, and some ephemeral storage. The idea behind this is that we have some pipelines that can be really long and take a lot of requests. and take a lot of resources, sorry, but most of the time they do not need those resources for the whole duration of the pipeline. They need them just for one specific step. And having multiple pods, multiple nodes, allows us to assign those resources only when they're needed. Next step, what we did after that. Dagster, I mean, I'm not a salesperson for Dagster. I just enjoy the product a lot, and I enjoy their open source community a lot. But the whole process that we have with Overstory and satellite images and so on is very complex. In particular, I mean, it turns out that when you deal with nature, some things are unpredictable. For example, if there is a storm, you're not getting satellite images on that day. So you come back the day after. But there are some other struggles that we had with Dagster in particular and the way we've built our infrastructure. The first one was observability. Dagster is a nice web interface that allows you to see all the pipelines that you're running and how they're going and what is failing and why and so on. But as we were growing, having sort of like aggregated statistics per team, how many pipelines are failing for this particular team or this other team, those statistics were difficult to extract. And also, we started having more and more complex dependency hierarchies. And some retry logic can still be difficult to model with the native Dagster. Before, there was a super interesting talk about assigning resources for CI jobs, which was extremely interesting. In our case, the problem that we have is that sometimes the same job can take a considerable different amount of memory or CPUs depending on the input files that we have. So, using statistics from like a previous run of the job is not always accurate in our case. So what we've done is that we have built something on top of Dagster, which is what we call our platform. Let's put it this way. So in the lower part of the slide, you still have Dagster, which is still our workflow orchestrator by all means, and Grafana that we use for monitoring. But then a different team, I'm part of the SRE team, the platform team has built a set of components that they are used to manage and schedule these jobs in a certain order based on the complex conditions that we have. Those are 4 different types of, sorry. Those are 4 different microservices: starter, the router, the trigger, and the watcher, that trigger the jobs with certain inputs and certain configurations based on what we need to achieve. All that communication is done using Google PubSub and OpenTelemetry, and this allows us to have some nice dashboards in Grafana that show us the state of our scans, pretty much. And this allows us to have something like this. So whenever we have a new scan request from one of our clients, we can track the process end to end and really show, okay, this run is waiting for images. This one is processing. This one is waiting for the output, and so on. And we have this whole overview running in Grafana thanks to our platform team. Okay, let's wrap it up. Right now, our platform, this is a message of just a few months ago when we put the platform live for our first, scan, let's put it this way. We managed to basically redo a previous scan that we had done, no touch, in 30 minutes, which is fantastic. I mean, considering how manual that process used to be in the past, this is a great result. And as of today, I think like all of our scans are processed using our platform. We are constantly improving it. We are still fixing bugs. We are still, trying to, work out some rough edges, but it's a great result. And what we are looking for with this is, first of all, to deliver results to our customer as hands-off as possible. We would like to be we want to avoid any manual step that goes on with delivering a scan to our customer. We want to take the platform and the Dagster automation to the next level and also build on some newer Dagster feature that they've released in the past couple of months to make the automation even more solid and robust. We would love to break the one step, one node, or one job, one node abstraction. So currently, every step or every job takes up one full dedicated node. This works okay for now, But I feel like there must be a better way of doing this. We are looking into GKE node auto-provisioning, meaning that in this case, it will be GKE that creates the node pool for you so that you don't have to hard code anymore the size of your pools. And another problem that we are facing and we are currently improving on is avoid as much as possible under-provisioning or over-provisioning resources. Under-provisioning is a problem because if a pipeline like the one that we run goes out of memory like after 6 hours, very often you need to restart from the beginning on a bigger machine. Over-provisioning is exactly the opposite, so you allocate more resources than the one that you need, and that's more of a matter of cost. The idea here would be to make the Maple API a little bit easier to use, where our developers need to guess a little bit less which node pool they need and how much CPU and memory they need. But it's a complex problem. And in this case, also the pod auto-resizing might be an interesting feature for us coming in Kubernetes 1.33. And of course, we keep on improving on monitoring and observability because without data, making improvement is really complicated. And with this, thank you very much for your attention. In case you're interested in connecting, my name is Andrea Giardini. You find it over here. Overstory is hiring, so overstory.com/careers in case you're interested in the problem of wildfires, in case you're interested in working on this kind of complex problem on a type of data, satellite images, which is definitely a non-traditional one. Thank you very much.
Awesome, thank you very much. There is room for questions. Oh, up there.
Up there, yeah. A couple of more throws. Nice.
Thank you, Andrea, for this interesting talk. We have the policy of chaos engineering within our company. Is Dagster able to resume a job if the pod gets killed?
Is Dagster able to resume a job if the pod gets killed? Yes, but you need to go into, you need to do some checkpointing, right? So the idea is whenever, let's say that you have a job that has like 3 different steps, you need to also code your job in a way that, okay, if steps number 2 get killed, I'm not restarting from the beginning, but I'm starting like alpha way. So when the temporary files of, where the temporary results of step number 1 need to be stored somewhere. So yeah, it's definitely possible. You need to code it in a way that makes it possible.
More questions. Down here.
The question is, how do we get our satellite images? Interesting question. I also didn't know that before joining Overstory. But basically, there are a set of satellite images provider, Maxar, like big companies like, Maxar is the first one that comes to place, that have satellite in space. And basically, you just order them. So you give them like the coordinates that you want, and you wait. And then after a while, you get the file. And yeah, I guess you can imagine that you pay by the amount of area that you request, right? But it's a little bit of magic, I have to say.
One more question. I'll give you my mic.
Yeah. We don't run our own satellites. We're not there yet, I'm afraid.
Non-technical question, but maybe you can answer. But are you more in like private or public sector, like in terms of customers of the company and what you do?
I would have to double check with, I would need to double check to answer that.
No worries.
But it's, most of them are like utility companies, let's put it this way.
Thank you very much, Andrea. Round of applause.